Well, thank you very much for having me here today. It really is a tremendous honor. USENIX really has a special place in this community and in my heart. To me, it's really the leader in open access, inclusion, and engagement, and it's something I've always looked forward to coming back to every year. I think this is my 20th USENIX security, and every year I'm blown away with just how much harder it gets to get papers accepted and how much more detailed the results are. And so it's very impressive what everyone here does. But I have to tell you, I don't come here just to read papers because I can do that at home. What I come here for is the conversations with faculty, staff, researchers, and friends. And with that in mind today, I want to have a conversation to you about building a world where we can trust software. Now, I truly believe that trustworthy software is one of the most important things that we can be working on, and that it's completely achievable. When we have trustworthy software, we get shit done. But when we don't have trustworthy software, we're always waiting for that next shoe to drop, that next bad EDR update to bring us down, the next distraction. It gets really exhausting. But when you do things right, you can focus on what you're doing. Security goes away, and you're only focused on the task at hand. It's one of those things that when done best, it's invisible to the user. Now, we need new advances in trustworthy software. And over the next few days, you're going to be hearing lots of great research on how to go about that. That's not this talk. This talk is about sharing with you some of my stories and trying to take that technology and get it into the hands of real users. One of the most influential papers I've read, and it's something I recommend everyone read, is a perspective by the Stanford research team who built a commercial tool called Coverity. It was one of the early and probably the most successful static analysis engines sold, and it came out of the Stanford research group working on a project called Metal. The Stanford Research Group had, at the time, a pretty radical view of how to go and make software more trustworthy. They threw out soundness and completeness and pushing Greek symbols, and instead, we're just going to measure our tools based on the number of bugs found. After they had founded the company, and right before they had an acquisition for $300 million to Synopsys, they wrote a paper, and in that paper, there's this beautiful quote that says, "However, the problems we encountered were not the obvious ones." Well, often the problems we encounter aren't the obvious ones. Over the last decade, I've been bringing software security tools to market. We built something called Mayhem based upon 2 decades of academic research and lots of work bringing this into the market, first at the Cyber Grand Challenge, a DARPA challenge to demonstrate whether this technology works on a larger scale, and then into the hands of customers. And our customers include people like Cloudflare, Rivian, Boeing, Roblox, BlackRock, and Toyota. But things aren't always as straightforward as they look. And getting to this place where we had people adopting Mayhem, even though we thought it was the latest and greatest and most practical research, was a long one. And some of our problems were not what expected. So when I was thinking about this keynote, what I decided I wanted to do is just share with you 4 stories of problems that I encountered that were not the obvious ones. Things when I came out from my academic research institution and I decided I'm going to change the world by building a company around this, that I would have never expected would be a problem at all. So just 4 stories of these problems, nothing super fancy. I'll tell you what worked and what didn't work. And I'll try to point out some of the problems that we haven't solved and that I think are bigger community problems. The first story is called Understanding Their Wins. So the story starts when an SVP of a large aerospace company came to me and said, "We really need to increase the quality and safety of aerospace software. We're worried about it. Can you come in and help us?" And I got super excited. I love cyber physical systems. There's something really cool about finding a vulnerability in something that you fly to conferences in that's just exciting. So I said yes. I got on a plane, I went down there, and I did it. So the SVP had hooked me up with the local dev team that was working on various aspects of the system. And I don't want to go into too many details because of NDAs, but I can tell you it was critical parts of the system. So I show up with mayhem and all the academic hubris that we're going to come in with the best security tools and have a really amazing, successful time. So the first thing I do is I show up and I say, we're here to automate your security analysis. Just give me a Docker container and your executable code. Now, the way that we had built Mayhem was to analyze code much like fuzzing, and we had asked users to give us to us in a Docker container so that we could power up large CPU clusters to make the fuzzing goes faster. Makes sense, right? This is how you package software today. Of course, the engineer came to us and said, what's Docker? They don't know what containers are. And then he went on to say, we don't use that here, and do you handle PowerPC running VxWorks? Because you know what? That's what the software is written in. So I just waved that off, of course. Easy. He was not up to date on the latest tech, and so I just had to educate him. You can just cross-compile. And then I'll help you Dockerize. It's super trivial. It's just a 5-line configuration file. Our tools require this, so we scale analysis. Don't you want to use our tools? They're going to find great vulnerabilities. And of course, the engineer grumbles. Now, unfortunately for that engineer, the SVP had assigned him, and he knew the SVP was a friend of mine, and so he had to cooperate. But I could see deeply he was unhappy. So what was my mistake in this? The mistake I took away from this is I asked them to show work before I showed value. And this is one of the challenges we have when we're going out and saying, this is the latest and greatest thing, and if users do this one little thing, they'll get security. But asking people to do that one little thing before you show any value at all can often prevent you from taking off. It prevents that road from being traveled for the person. And it can be as simple as asking them to Dockerize their app. So as I started to work with them, I had realized that I knew nothing about how really embedded systems were developed. I had come in and I knew it was C, but I had to have this really quick education about how it was done. How many people here know how embedded systems are developed? Have hands-on experience? A fair number, actually. This is great. Well, I hope I get it right, because this is something I learned on really quick. The first thing when you're working with safety-critical embedded systems is you have to write out the requirements. See, embedded systems develop software in something they call the V model. Here we know it as waterfall, but they decided to put a little kink on it so it fits on a 4x3 slide. So developing with something called the V model, essentially waterfall. You write out the requirements, and requirements are the spec to them. And I don't mean a formal model spec, but I mean the engineering spec of what should be implemented. And this gets traced into a Word document, and that can often get traced back to the customer. Once you have those requirements, you start building up a model of what those requirements ask for. For example, this is a Simulink model for speed control in a car. The users, they go and they drag and drop their devices, and they plan it out, and then they do a model check to make sure their model meets the requirements for the spec. That's what they do. Once they have that, there's a little button there at the very top of the screen that says Generate Code. When you click that button, it creates the source code. Now, this source code is the most evil, vile thing you've ever seen. No human would ever write it. It's full of global variables. There's functions that are 15 switches deep or 15 if then else's deep, but it's, I guess, fine because it's generated code. And then this gets compiled to do a hardware in the loop test. This is where they want to run it on a PPC, for example. And the reason for that is because when you compile, the sort of errors that you could get at runtime will vary on architecture. For example, if you have divide by 0 on x86, you will get an exception on your Linux system. But if you're running on ARM, there is no exception with integer divided by 0. So they're trying to test for all these sorts of things, and that's why they want the processor in the loop. And then finally, they check these things out on the real deal. They say, fly this way, 5 miles, fly that way, 4 miles, and so on. So they had this development process I really wasn't aware of. And one of the things that stuck out to me, well, first of all, if we backdoored MathWorks and Visual Studio, or I'm sorry, MathWorks and Simulink, I'm pretty sure that you could own the world's software. Because as far as I can tell, everyone just trusts the generated code is correct, but no one has verified it. It's a great target for those insider attacks. The second thing that I observed from this is they're still generating C code today. We often read in the news about, hey, we need to get rid of C code, and what we need to do is go and translate the existing C code to Rust. There's a DARPA program that's coming up for this. And that is true, but I want to point out that for the embedded world, where there's a large swath of C, often if you target just a few tools and get them to generate safer languages, you would have an enormous impact, because people really, they're programming in this UI, not at the code level. So finally, working with this person over several days, we were able to figure out how to cross-compile, how to generate code that we could analyze, how to Dockerize, link that MATLAB code with their handwritten libraries, and start the analysis. The way Mayhem works is we spent years of doing symbolic execution research. And one of the things that we found in symbolic execution is it works best when you pair it with other analysis. In fact, when you pair it with fuzzing, you get the best results. There's a paper from the ASU crowd called Driller that also shows the benefit when these multiple analyses work together. I gotta tell you, the first time I did this, it was a bit of a psychological barrier. I had spent 10 years doing symbolic execution, making fun of fuzzing. And here it was, being a necessary component. So we built the product around that, because when you have actual customers, the rubber meets the road. You got to build what works. After you do fuzzing, there's a second step of doing diagnosis. Every once in a while, you'll get a Heisenbug from fuzzing and symbolic execution. But also, users want to get more information. Just telling people there's a bug is not enough. They want to know where it is. They want to know what type of bug it is. They want to know the severity of that type, because there's lots of bugs in the world. And at the end of the day, not every bug is going to get fixed. They're going to get prioritized. And so you need to diagnose, is it critical? Is it high? Is it low? And so on. And some of the ways, for example, we do this, if you're wondering how you do it, you can look at the type of bug. If it's an out-of-bound read, maybe that's medium. If it's an out-of-bound write, that's high. There's mitigation analysis that we do to see if things like ASLR and DEP have been compiled in. And believe it or not, if you compile in DEP and ASLR and other defenses, often it's OK in safety critical systems to still field the program, because there's a mitigation in place for exploitation. And then through all this process, we're generating tens, hundreds, millions of different test cases. We have to sum them up, because the next run that we're going to do with the customer, we want to reuse that test case to seed it off. And what you get out of this is better coverage, a set of POVs, proof of vulnerabilities, and a new test suite. So that's how Mayhem works. So I went up to him and I said, OK, we're running this analysis. It's the latest and greatest. It was proven in the DARPA Cyber Grand Challenge. It was exhibited in the US Smithsonian. And he asked me a very simple question. How long does it run? We have a lot of fuzzing papers here. How long do you have to run fuzzing? So my answer was, it depends. Programs have an infinite state space, so you have to make a judgment call. You're the expert. You tell me, how much risk are you willing to accept? And that is a stupid response, yeah. You're going to tell your boss that. We're going to buy a security tool, and that security tool can't tell us when it's secure. So we have to be very opinionated on these things. And this is one of the hardest things when I transitioned from research into industry, to stop giving technically correct but useless answers. They are the worst. People turn to us to provide this sort of guidance, and you turn them off when you can't give concrete answers. Now, we all know, if we want to put on our scientific hats, that static analysis can have false positives, and that dynamic analysis can have false negatives. And we can talk about the various problems on that all day. What question they're asking is, when can I get shit done? So I finally got through this and said, we want to run it until you saturate coverage. And we found bugs. We found places where it looked like cyber attacks were possible in critical components. I want to call them bugs, because until you go and you show the full chain exploit, you'd never want to call something an exploit or vulnerability. As soon as you do, you're going to get shut down into another process. If it's in a DoD system, for example, it becomes secret. If it's in a commercial system, all of a sudden the lawyers have to worry about, is this a recall? So instead of saying you find vulnerabilities, you find defects. Now, when I said this, He said, that's impossible. We have proven safety. And one of the things that I've learned in industry that was really unusual, it really hit me kind of oddly, is there's two different standards everyone does in embedded systems. There's a safety standard, and there's a security standard. And so you can get up as a vendor with 100% authenticity, say we're 100% safe, and at the same time say we're 100% insecure. Doesn't that just blow your mind? Like in classes, we talk about safety properties as security properties. Security checks safety properties, right? But no, not in these industries. Now, I know Kevin Fu in the back is railing against this because I would say the same thing that he would. Security works differently. What you're proving in safety is typically around random failures, not against an attacker. And that's what makes this field unique. When people ask, why is computer security a unique field of computer science? It's because we're the only one that has the presence of an attacker. That's what makes us different. And the response is, we'll look into that. Again, no motivation. This was going terrible. The lesson I took away from this was my win wasn't their win. I came in and I told them, I'm going to find bugs. I'm going to ask you to do work. I'm not going to give you an answer at the end of the day whether it's insecure, but I can call your baby ugly all day long. So what saved the deal? This is a customer of ours today. So if you look carefully at how analysis works, symbolic execution and fuzzing, there's a core idea. The core idea is untested code is risky code. You run the program, the analysis identifies untested paths, and it writes tests for them. At CMU, we had a fairly infamous hacker named George Hotz. He did the first iPhone jailbreak. He did the first Sony PlayStation hack. He's done lots of crazy things, trust me. And he told me the way he goes and finds 0 days is he looks for the untested code. It's as simple as that. That's where the risk lies. And so, of course, these analysis, what they do is they try to identify it in symbolic execution. We'll model path constraints. It'll build formulas and generate inputs that take you down that path. If you're doing fuzzing, you have heuristics. Same thing. You're looking for new coverage to get rid of those risky paths. And then you just iterate this forever until you find a defect. And if you go read a USENIX security paper, if you go read an industry paper in security, they're going to point out the CVEs that they found with this. But there's actually two things that you get out of this process. You get an input that triggers a defect. That's right. We call those proof of vulnerabilities because it's great marketing. But you also get a test suite. You've now expanded coverage, and you can reach more statements than you could before. And that, my friends, is part of their safety standard. How much and how well it was tested. So I said, by the way, we have just now got 80% assembly coverage. And it was free. It was something that we did over a day, and he was just blown away. Behind the scenes, they had budgeted $10 million to achieve that same coverage at the assembly level through manual analysis, and we handed it to them for free. I was pretty confused at first. Why is he so excited? And it's saving them thousands of hours, and it was almost an artifact of security. So in this entire talk, there was a point I was trying to make. It wasn't that the engineer was wrong and I was right, or vice versa. It was that when you're trying to create trusted software, it means tying security to their goal. The goal of that person, if I had bothered to ask at the beginning, was he wanted to increase coverage. That's what he was getting evaluated on. That's the task he wanted to do. And when I was able to explain how security helped him achieve his goal, we got adoption. Far too often, we speak like I spoke to the SVP. Think of all the risk if there's a security disaster. Think of that company and all the problems. You could have recalls. People could die. There's money that could be lost. But at the end of the day, the developer who's doing the work, the one responsible for building that trusted software, he just wants to get his job done. Let's figure out ways to help him do that better. So the second story I want to talk about is building community. I'm a big believer in community and the power it can have because it gives you a unique place where you can talk about things that interest you that maybe don't interest anyone else, and it gives you a new set of friends to go back every year, like here at USENIX. I want you to meet GeoHot. So I alluded to George Hotz, the world famous George Hotz, who has done crazy things. Currently, his goal in life is to retrofit autonomous driving into legacy cars. He's hacking with the CAN bus in a very unusual way where they have vision and send messages over the OBD port to self-steal legacy cars. He is probably one of the world's best hackers. When I came to CMU as young faculty, wanted to be part of a world-class hacking team. I wanted to be like George Hotz. The challenge in all this, though, is finding people like George and building such teams is incredibly difficult. We have a small pre-existing talent pool at Carnegie Mellon University. It's a very large time commitment to do this. And it's a regular 4-year turnover. We have, of course, undergrads who come in and do this, and they turn over. And so the question is, how can you build a team looking at cybersecurity and being able to elevate themselves to that level of George Hotz, given these challenges? And I got some inspiration from a guy named Jordan Weens. Jordan Weens is probably the nicest person you'll ever meet. He runs a company called Vector 35 and makes a tool called Binary Ninja, if you're a binary analysis person. He was my inspiration, and one of the things he was doing on the side was mentoring local high school students. And the way he was mentoring them in computer security is he was building games called CTFs, Capture the Flag competitions, where you'd give people a small, interesting problem and let them have at it, and when they solved it, you could auto-check the answer. So for example, you might give them a question like, how many bytes are needed to return the return address? And if a user inputs the right answer, they get points, and you've gamified security. It's a little bit like the concept of NP hard, because finding the solution takes a long time for the person, but checking the solution is easy. You just have to check the flag. So we built something called Toaster Wars as part of this idea of let's build a CTF. Let's try to follow after Jordan and what he did so amazingly to motivate so many students. But we ran into a problem of how do we attract people? Now, there is a law of large numbers. When you're in business, you spend a lot of time talking about the marketing funnel and the sales pipeline. The idea of a funnel is at the very top, you have people who are aware of what you're doing. You have people who enroll in what you're doing. You have people then that try doing something. And in CTFs, we count people who have the first solve. They've actually participated and put time in to solve a problem. And then they return to your solution, and in a CTF, there's win. And the reason we call this funnel, right, is because not everyone who is aware of the contest is going to play. Not everyone who's going to try is going to win. But there is a law of large numbers. The larger the size of that funnel, the more people you will get in to win, and the larger the probability of identifying the top performers. At the time, I had a PhD student named Peter Chapman. And I'm very thankful that he helped me with this problem, because he pointed out something I never would have thought of. I was like, I'm going to build this game. I'm going to emulate Jordan, and everything will be awesome. If I put it out there, they will come. But he told me I have no funnel. More importantly, he proposed a way to get it. What Peter did was he mined Wikipedia for the state teacher mailing list. He then told the teachers there's a 1 week worth of hands-on lessons and that they didn't have to do anything. Nothing. Zero software to install. They just went to a website, and we had CMU academic curriculum and a fun contest for them. And we gave teachers a way to record class participation. You'll see a hint here of what we were trying to do. We were trying to solve the teacher's problem, not our problem. We were trying to give them free curriculum. In year one, with this method, we went from an unknown contest to having 30,000 active players, people who solved at least one challenge on that. If you think about it, reaching that sort of crowd in that sort of time, it would have never happened without Peter's insight to go after the people who had the connections to our market. Today, we've launched Pico CTF. We have over 400,000 people who have done it. When I go and look at it, it costs less than a pack of gum per student. I'll tell you, one of the things I haven't solved is how to fund this. One of the challenges I think we have in a security community, especially the nonprofit, is doing this sort of work is incredibly important to grow the field and build that next set of developers who can develop secure and trustworthy software. But we don't want to treat these as research experiments. We don't want to necessarily go out and treat the people playing as subjects. What we want to do is engage them in our community as participants. So today, very successful on the surface, still have no idea how to fund it. Jan, I'm going to go find you later on because you seem to have it figured out. I got to brag because these are my students. We just got back from DEF CON where we ran our 8th DEF CON CTF. At DEF CON is a hacking contest, very different than this contest. But if you win the DEF CON CTF, you get lifetime admission. No more conference fees. They're called black badges. You're called inhuman, actually. There's even a separate line you go to. We have 64 of these badges now. We have a Christmas tree of these. Everyone on our team has them. And if you go look at the sort of impact for making the world's software safer, I went and I looked at the picture and who's in it. We have in this picture the head of Google Threat Intel for China. She learned how to secure software and about security through Pico CTF and CMU. We have a CEO of a blockchain company called Theory. We have a researcher at Microsoft Research. We have a pwn-to-own browser hacker. This guy, I don't know how they do it. We have CVEs. This guy owned in the latest pwn-to-own Safari and Chrome and made like $60,000 with the bug bounties from that. We have the first Tesla hack, which was done by a person about 4 years out of high school who learned about computer security through this. We have a UCB HCI professor, the DoD. I leave the word DoD there because we don't want to talk about who it really is inside the DoD, as well as AIXCC for the new cyber challenge, developers, and I just found out qualified. So if we really want to make a world where we can create trusted software, we have to find the communicators. We can build the platform, but the key to the success for all of this was talking to the high school teachers and really figuring out how to use them to connect us to the people who were interested in what we were doing, were aware, and had the time. So to build trusted software, find those communicators. We recently used this approach to solve one of our problems on open source. Mayhem runs on code, but the first thing we have to do, as I mentioned, is Dockerize that code. Now, most people don't Dockerize. I remember I went to DockerCon, walking around the conference, and everyone I talked to was there to learn about Docker, not because they were using it. And so what we found using this principle is that we could go to colleges and we could offer $100 for taking an open source project and building in a CI/CD pipeline to run Mayhem and other security analysis. And so for a few $100,000, we've been able to get 2,000 open source packages up and running. I put this up here because I think it's an interesting community resource. Often we want experiments, and because these are all Dockerized, they all have harnesses, you have an area where you can run your data set on something much larger and potentially get a much bigger signal for the sort of research you're trying to do. So the message here, go find the communicators. This is going to be the hardest part of my talk because it's probably where the most difficult part of the learning is. It's almost an experiential learning. But I want to talk to you about segments. If you go read blog posts from Google or reports from CISA or DARPA CFPs, you'll come across a statistic something like this. Roughly 70% of all software vulnerabilities continue to be memory safety issues arising from the use of memory unsafe programming languages such as C and C++. I'm going to tell you, I think this is suspect. I'm not sure it's true. When you go back and look, it says something like to the original sources in Google that Google saw most of the exploits against them using these. I'm not sure it's true. But whether it's true or not, I want to tell you why you can get the wrong message from this and why we had it as well. We had just won a massive challenge. We had incredibly high egos at the time. We thought we were solving a problem that was the 70% problem, the large problem. And so, of course, we could walk into any room and sell Mayhem. We could transition our tech and the world's software would be safer because a new person was using it. But it turns out that assumption was completely wrong. The world is not full of C and C++ devs. The world is not full of companies who care about memory safety vulnerabilities. And it took me a long time to find out why. I had to rail against this for a while because surely it must be true. This is a graph from a company called Slashdata that monitors the developer community. And if you go and you look at this, this is a developer population by language choice. You'll see JavaScript, of course, is the most popular. But if you dig into the numbers, it turns out that 87% of the developer community does not use C and C++. And so if your research is focusing on C and C++, you can't say that it's going to be the most widely applicable. You can't. Now, I'm not saying it's not important. It is important. But it goes to show that there must be other important things. The right side of this graph is also very important when you look at this. When we look at areas like cloud security and machine language, it turns out, machine learning, it turns out that the language you pick is often picked based upon the project type. The reason this is important is if you're doing web security, you're looking at Python code and JavaScript code. In fact, if you're looking at web security, you're going to find there's about 3 times as many customers as C and C++ code, if you look at those numbers combined. You'll also find that there's different security properties that you want. When you go look at web server or API security, what you're actually looking at are things like SQL injection, XSS, and so on. You're looking at reactive systems. You're looking at systems that store information in a database. These are all techniques that are traditionally hard for things like fuzzing. Imagine you have an API where you put an item in the database and then you remove it, and then you can do an XSS attack. I've seen this happen. These sorts of stateful attacks are really hard to reason about today. Very common here. The other thing that we learned when looking at these projects is the type of project actually has a strong bearing on whether companies feel it's security relevant, and that's because of this attack surface analysis. When we went and talked to companies about C and C++ and memory safety vulnerabilities, one, there's a bit of a tragedy to the commons for open source. If they're using open source, it's not our problem. Open source maintainers will fix it. But also, most of the code that company is being developed is on the web using one of these web languages. It was something kind of non-obvious to me. I would look at memory safety and what if it got exploited, you could do a full control flow hijack, and that was the way I thought of it. I think the way companies think about it is actually a little bit better. They go and they look at what's on the attack surface, and certainly if it's web and API, it's out there. And those are the things that they're focused on most. So if you want to have an impact in making software trusted, I would say that you have to look at both what types of projects people are building and what languages, and make sure your research addresses those. Now, when you go into industry, you'll also find with this language that their idea of an app is not one single executable. Nothing like it. If you go to Roblox, one of our customers, their app on an iPhone or an iPad or a PC is compiled C code wrapped in a Lua interpreter. Do your techniques handle C++ code with a Lua interpreter? So we're able to check that. But the back end is actually what they care about. If you can hack an iPad, all of that information gets transmitted up to a cloud via a web API, and that's where they do things like making sure that you're not going after kids, making sure that you're not cheating the system, doing all the payment transactions. And so while they care about that code on the top, the code on the bottom is what they care the most about. And preferably, they would like to have both. We see the same thing, whether it be Roblox, or I just put up another example, Rivian. Onside the car, they run things like RTOS systems. It runs infotainment, which is a real Linux system. That gets connected to the cloud. The real attack surface that they see is those back-end infrastructures, because everyone on the internet can hit them. Well, if you can compromise a car, well, you're just compromising one car. So look at the problem domain. When I went into customers, first I thought it was all C, C++. The second mistake I made is I thought the academic definitions, or actually the scientific definitions, would really drive purchases. There's really 2 choices in this conference that you can look at. You're either doing a static analysis or you're doing a dynamic analysis. And because of undecidability, you're going to have false positives with one and false negatives with the other. And you're trying to always minimize this inside your research. So when we came into industry, we thought we had a very novel proposition. Dawson Engler, when he broke into the market, he was using static analysis because you could scan all the code. But you do have false positives. So we came in hot and hard with the 0 false positives. And people really do care about that sort of thing. But this graph misses an important dimension. This graph is showing the technical trade-off between 2 techniques, but the other dimension is time. Are you looking for previously known vulnerabilities or novel vulnerabilities? And if you think about it, the number of vulnerabilities discovered is going to accumulate over time, and it's going to be the largest amount. So accurately detecting previously known vulnerabilities is probably going to have a larger impact than finding new vulnerabilities. You need both, because people continue to write new code. But finding old vulnerabilities is by far just a solved problem, because you still have to be able to find them accurately in the code. Now, I threw in this slide because I realized I was going to use terms that people may be not familiar with. But one of them is called the SBOM. We hear a lot of work about the SBOM, and technically there's something on top of that called the SCA. The SBOM is simply a software bill of materials. Think about it as the list of dependencies if you write Python. Here we have Fast API, we have Unicorn, we have Pydantic. The software bill of materials includes that list. On top of this is software component analysis. Software component analysis tells you which versions are vulnerable. For example, software component analysis could say Fast API version 0.111.0 has a known vulnerability. Very simple analysis. You take one file, you look at the version, and you tell people what they have. There's an entire market here for this. So while I came in originally thinking I'm going to look at false positives and false negatives, I think the right way to look at it is, are you looking for unknown vulnerabilities or known vulnerabilities? And the first thing a company wants to do to make secure software is make sure they don't have known vulnerabilities. It's actually somewhat nice, right? Like, we should make that our base. There's no more known vulnerabilities. And then they want to invest in finding unknown vulnerabilities. If you go look at this market, this term SBOM SCA has created probably the most successful software security company out there, at least by value. And it's called Snyk. Snyk is worth $7.4 billion today. To give you a sense, Coverity, which did static analysis, sold for $350 million. Because they were looking at this problem of how do we make sure we can accurately detect what vulnerabilities already exist and make that user experience so easy. So my mistake 3 was also not understanding the motivation for these tools. So when we talk about when things are real, whether it's going to be something you can use in real life, you have to look at the motivations people choose to use them. SBOM SCA is incredibly easy. You point people at the requirements.txt, or your package lock if you're doing JavaScript, or your built-in dependency manager if you're doing something with C and C++. Static analysis is legacy. It is the tried and true. It's the you can't go wrong with IBM. Dynamic analysis is the new kid on the block. It's test-oriented, which means you actually need a runtime environment to do it. And scanners allow people to remotely check. Now, the reason I have these on here is because they give you different flavors of the types of goals people can have. When you're running a static analysis, you can run it across all your code bases at once, and you know when the scan is done. When you know the scan is done, you now have a gate to know when you can ship software. I could have answered the aerospace engineer, run the static analysis, and when the report is clean, it's good. When you're looking at dynamic analysis, you're looking at test-oriented methodology. And that test-oriented, you're going to say, well, it's never done, but you get high accuracy. And so what we tend to see is that companies will prefer one or the other, depending upon whether they have this false positive or false negative fatigue, but only for new vulnerabilities. On top of that, they will always layer in an SBOM looking for known vulnerabilities. And then they will engage their security team with scanners. Typically, your security team inside industry is not connected to the developer. Say it again, typically the security team has nothing to do with development. They're running your SIEM, they're running your SOC, they're setting up your networks, they're doing incident response. Those are the sorts of tools that they're going to use their scanners. So we had to iterate. We went to the market with C++. We had to focus in on a segment. That segment was people building embedded systems, people who were developing high-performance networks. That's why Cloudflare is one of our customers. But we had to add to our tool set to cover these other use cases. Otherwise, people wouldn't adopt. So we had to add an API tool. The reason we added an API tool was to handle those Python and JavaScript languages, because what most people were doing were building APIs when we went and looked at it, at least what they cared about securing. We also had to add an SBOM tool to cover that problem of known vulnerabilities. And the problem we tried to tackle in this was, how do we remove false positives from this? So when you run an SBOM, you often end up with, well, false positive is the wrong word, useless but accurate results, let's say. If you go pull the Postgres database today and you look at an SBOM report, it will have the highest CVSS score you can find, 10.0. If you pull Redis, same thing. Just pull the latest Docker image. It looks like the sky is falling. But that's because the apt program manager happens to have a CVSS 10 vulnerability as of earlier today when I checked, and it's in there. But apt isn't on the attack surface, and so it really doesn't matter. And so we developed something that would take an image and try to determine what's on the attack surface of those known vulnerabilities. That has been incredibly successful, but also something we would have never expected going in. So the story is really about solving per use segment. When you look at a web developer, they're writing software, and all software in Python, JavaScript, and C, it's all Turing complete, so you might think it's equivalent. But you really do want different techniques because the type of application they're developing is different, and the way they adopt security tools will change. So let's focus on how they're using them in this segment. So I want to spend the last few minutes talking about, I think, the most important thing that I found as we want to build a world with trustworthy software, and that's to keep moving. This is the part where I tell you my personal story. So I have never, when I look back, my path was never supposed to be an academic. I had dropped out of high school. I lived with a meth dealer. The meth dealer got arrested one night, and I realized that that was a very bad place to be, and I went back and got my GED and got into the easiest college in Colorado, University of Northern Colorado. After that, I worked at Stanford, and I applied to the Stanford PhD program, and I was rejected. Now, this is USENIX security, so I will say something. I actually got the Best Paper Award with Dan Bonet and was still rejected for my PhD from Stanford. I finally became faculty, and as we were doing work in automatic exploit generation, this work was completely roasted. For about a month, there was a guy named Dave Eitel who would go off on how useless this code was and how I knew nothing about exploitation. Despite we had DEF CON black badges, he would go off on that. And I was really upset with him at the time. And I think he made some very terrible points on why this research wasn't reality. But I think what I took away from it was to also have an idea of what industry thinks is not necessarily what we think. And then a few years ago, I kind of disappeared from this conference because I had a cancer diagnosis. I went through radiation, I went through a major surgery, and I drank through a straw for about 6 months and finally recovered. So throughout this, I've been doing 20 years of research in program analysis. And if you look at this, there are ample reasons to believe that I shouldn't keep pushing forward. But if I did that, I would have missed finding my passion in computer security when I went back to school. I would have missed finding my advisor, Don Song, who was absolutely the perfect advisor for me. I would have missed competing in the Cyber Grand Challenge and showing Dave Eitel that DARPA had at least accepted my research as being important. And without the cancer diagnosis, going through it, I wouldn't be here today. So there's going to be a lot of pitfalls. There's going to be a lot of roadblocks. There's going to be times in your research where things don't seem to be moving forward. But you got to keep moving because those are all temporary. So the last thing I think we need to create trusted software is to keep falling down. You will fall down, but to keep getting up. Don Song told me something that stuck with me when I was a young graduate student. Don Song, my advisor. She said research is really about dropping pebbles to cross a river. You keep dropping them in the stream, and eventually you end up with a bridge. Sometimes those pebbles get washed away. Sometimes you can't see the old ones that you had, but it's important to keep dropping them if you want to build that bridge. So keep getting up. Be like Don. So in summary, I think creating trusted software is something that's so important for all of us. But I also think it's entirely doable. If you go look at the statistics, if we simply took the top 1,000 GitHub repositories and we secured those, we would have secured over 70% of the code people are using to additionally build on open source projects on GitHub. So it's just 1,000 projects, right? If we all sat down for a few weeks, we should be able to accomplish that. So it's something entirely doable. To do it, I think that we have to go beyond just the latest techniques, though. We have to tie security to their goals. We have to find the communicators who can help us get in front of people and amplify the message. We have to solve per use segment, because what's going to work for a C++ developer is not going to work for a Python developer. And then we have to keep pushing because people will not necessarily adopt things on our time frame. They're going to adopt them on theirs. And as we go forward, we're going to run into personal roadblocks. But all these things will go away if you keep getting back up. So throughout this, I wanted to provide a TLDR. In this talk, everything I've talked about today is really about solving their problems first. That very first thing that I mentioned where we have this engineer and he was excited about coverage, if I had solved that problem first, I would have had instant adoption. Instead, I had to fight my way into it. When I talk about expanding the set of security talent out there, the problem I solved was for the teachers. And if I hadn't solved that problem for the teachers of having free curriculum and making it so they had a week where they had less work, I wouldn't have been able to reach the students to read to grow it. When I think about the segments is all about solving what problems they think they have. The Python developer is gonna have different problems than the C++ developer. You need to focus on what their problems are in that community. And then finally, you should be solving the problems that they're looking on, but you need to keep going. As you're doing it, you won't get it right the first time, but if you keep working on it, you'll get it right eventually. So that's what I had today. 4 quick stories about where I try to take technology, get it adopted, and some of the lessons I've learned. Thank you for listening.